Hi everyone. So in my previous lecture, we were we were discussing about some questions regarding transforms, like what is a transform, why do we take a transform, which are the other transforms, and how many transforms are possible for the given class of signal. And in the previous video, I have discussed what is a transform in general and why do we transform a signal. Now today in this video we shall address two more questions which were asked by you on my video on introduction to Z transform. So the next question asked was, which are the other transform, other other than Z transform. This is the question number one. And question two, how many transforms are possible, or you can say available, for the given class of the signal? So first I will answer the question number two. As we saw in the previous video, that transform is nothing but change of basis. We represent a signal in terms of some other signals, and these other signals are called bases. So transform is what, in short we can say, transform is nothing but change of basis. Now, how many bases are possible? How many bases are possible for the given class of signals? In other words, how we can express how many different types we can express a given class of the signal. So the answer is there are infinite ways. The answer is there are infinite ways, because there are infinite bases are possible. So if I ask, is there limited number of representation of the signals or for the given class of the signal? The answer is no, it is not limited. We can have, in principle, infinite number of representations or infinite number of different transforms for the given class of the signal. So now I will address what are the other transforms other than the Z transform. See, these bases which we have to select for representing signal depends upon, number one, the class or the type of the signal, and number two, it depends on the application at hand. So there, what are the other types or what are the various available transform? This will depend upon type and application. Now, generally, signals can be classified into two types. You might be aware of this: continuous time signal and discrete time signal. These are the two broad classes of signals. And now I shall discuss what are the popular transforms available for these two general classes of signals. So first in brief we see what is a continuous time signal. Let's say x of t is a signal. Where t is independent variable, you can assume t is time, and x is dependent variable, you can assume its amplitude of a current or voltage or temperature. And let's say this x of t is like this. Now if this t belongs to R, that is set of real numbers, and if x is defined for all these values of t, then we say that this t is taking a continuum range. Let's say this range is between 0 and 5. So if I ask how many real numbers are possible between 0 and 5, so there are infinite real numbers, and at all those real time instances this x is defined. So t is taking a continuous range. I can say t is continuous because t is real. So this kind of signals are called continuous time signal. On the other hand, if t is not continuous, if it is discretized, for example, let's say you have independent variable t, but this t does not belong to R. Let's say t belongs to set of integer. And if again I define some signal, let's say between 0 and 5, then at what time instances my signal would be defined? My signal would be defined only at integer time instances. That is at 0, 1, 2, 3, 4, and 5. If somebody asks, what is the value of my signal at 0.5 or 1.2? The answer would be, it is not defined. It won't be 0. So there is a difference between not defined and 0. So let's say I define my signal, let's say 2 at 0. It is, let's say, 1 point minus 1.1 at 1. Let it be 2.9 at 2, at 3 let it be 0, at 4 minus 1, and 5 let it be 4. So this is a signal, and this is a sequence of number you can see. So this time t is discretized. My x is defined only at finite number of time instances. So therefore, this kind of signal is discrete time signal. This red signal is continuous time signal, and this discrete time signal is what? It is nothing but it's a sequence of number. You can write xn is a sequence of number like this: 2 minus 1.1, then 2.9, then 0, and then minus 1, and then 4. So it's a sequence of numbers. So discrete time signal is a sequence of number, whereas continuous time signal, it's a function of time, continuous time function. There I am not putting any restriction on amplitude. X could be discrete or it could be continuous. Similarly, here also x could be discrete or x could be continuous. So now we have two different classes of signals. One class is called continuous time signal and other class is called discrete time signal. Now, as I have explained that infinite number of bases are possible for both continuous time signals as well as for discrete time signal, and therefore there are infinite ways, or there are infinite number of transforms are possible for the given class of continuous time signal as well as the given class of discrete time signal. But there are certain popular transforms which are used, and which transform should be used, it depends upon the application. Today I will also list down some important transforms or the popular transforms which are used for continuous time signal and discrete time signal. So I make a table. Here I will write continuous time transforms. Continuous time transforms which are popularly used. And here I will writing discrete time transforms which are generally used. So can anybody guess which transform is the most popular for continuous time signal? So you are right, it is the Fourier transform. So the first transform, I can call it continuous time Fourier transform. I am simply writing abbreviations. So CTFT or simply FT, it stands for what? It stands for continuous time Fourier transform. This transform was invented by Fourier Joseph for solving some equation when he was studying heat flow. So it is, I can say it is one of the oldest transform available with us. And here in this transform, if somebody asks what is the basis, so basis here is sinusoidal functions, and the sinusoidal functions are everlasting function. Everlasting functions means they exist from minus infinity to plus infinity. So here the basis is set of sinusoids of various different frequencies. So this is the one of the oldest transform which we use for continuous time functions or continuous time signal. Now, is there any corresponding transform for discrete time signals? Yes, it is. And this transform is called discrete time Fourier transform. In discrete time Fourier transform, again, the basis function or basis is what? Sinusoids. So what is the difference? In continuous time case, basis are sinusoidal functions. Whereas in case of DTFT, what are the basis? Basis are sinusoidal sequences, not sinusoidal functions. Now, this DTFT is not discrete function of frequency. It's a continuous time function of frequency. So it can be discretized. And if we discretize discrete time Fourier transform, we get something new and it is called discrete Fourier transform. So there are two types of transform where basis is what? Sinusoid. Discrete time Fourier transform. Discrete time Fourier transform here, omega, which is frequency, it's a continuous function. And here x of k, where k is the integer. So this is one of the popular transform used for discrete time signal. Next popular transform is Laplace transform. Here the basis is what? Basis is exponentially decaying or growing sinusoids, not sinusoid, but the exponentially growing or decaying sinusoid. So I won't go into the detail. My intention is just to mention the names of important transform. So the Laplace transform is the transform which is used for continuous time signal. So is there any analogous for Laplace transform in discrete domain? Yes, it is. And what that transform is called? This transform is called Z transform. So the discrete counterpart of Laplace transform is what? Z transform, which we are studying. In my first video, we studied Z transform. Then the next important transform which we use is called Hartley transform. It is nothing but a variation of Fourier transform. Now this CTFT, it's a complex function of omega, whereas this Hartley transform, it Here again, bases are sinusoids, but this Hartley transform is real, whereas this CTFT is complex. Now you can have discrete Hartley transform as well. Now then there are transform which are called cosine transform. Again, it's a variant of Fourier transform, but here our basis function are cosine function instead of e to the power j omega t, which is a complex sinusoid, which you can say it's a basis for CTFT. Here you can say cos omega t or sine omega t, where omega can take any real value. So these are the basis. So cosine transform, or one can also say sine transform. And discrete counterpart of cosine transform is called discrete cosine transform. It is used in some compression techniques. So discrete cosine transform. Next transform. Now it is very important to note that in these all transform which we have listed down here, when we are transforming a signal or a sequence, we are moving from continuous time to frequency time. Signal is transformed from time domain to frequency domain. But there are transforms which can transform a given signal from time to time and frequency jointly together. So those transforms are called time frequency transforms or time frequency representation. There, in those cases, your transform would be not only function of frequency, but it will also the function of time. So to plot that time frequency representation, you will need a 3D plot. So now we are going towards time frequency representation. So the simplest time frequency representation is called short time Fourier transform. This is nothing but the windowed Fourier transform. We perform the transform over the small segments of the signal. So here again, the bases are sinusoids, but not everlasting sinusoid. Here we can say the segmented sinusoids are basis for STFT. You can have discrete version of STFT. So discrete STFT you can have. Now if we go further in time frequency representation, there is an important class of transform. There is not a single transform, but there is a whole class of transform. And that class of transform is called wavelet transform. These are very popular transform, and they are used in almost every domain, not only in electrical engineering, mechanical engineering, automobile engineering. They are used in various applications. Now they are used in biosciences as well. Now, wavelet transform, as I said, there are different variants of the transform. You can have infinite number of wavelet transforms. So, like the important continuous wavelet transform are Maxian head transform or Morley transform or the Gaussian transform. These are the some important continuous wavelet transform. Now there is a variant of wavelet transform. It is called wave packet transform. Now question comes, do we have a discrete counterpart of wavelet transform? Yes, we have, and we call them discrete wavelet transform. What we call them? This week, the continuous counterpart is called continuous wavelet transform, and this is called continuous wavelet packet transform. This is discrete wavelet transform, and similarly we can have discrete wavelet packet transform. Now, these transform can also be classified as linear and non-linear transform. So till now, the transform which I have listed, all they are what? They are linear transform. Now we can have some other transforms, which I can put them in category of non-linear transform. Again, here I will mention transforms for continuous time signal, and in right hand side I will mention transforms for discrete time signal. So the next important transform, which is again time frequency representation, it is called Cohen transform. And the next transform, which is again a time frequency transform but non-linear time frequency transform, it is called Wigner-Wille distribution. So these are the time frequency representation where time and frequency comes together. Now there are certain other transforms in like where bases are some other kinds of signal like Walsh transform. This Walsh transform is not time frequency transform. It's some different kind of transform where our basis functions are neither sinusoids nor some segmented sinusoids. They are some orthogonal set of functions, some other orthogonal set of functions. So other important or popularly used transform for continuous time signal is Walsh transform. And discrete counterpart of Walsh transform is discrete Walsh transform. And very similar to Walsh transform is another transform in discrete domain, which is called Hadamard transform. Now one may ask, is there any discrete counterpart of Cohen transform or Wigner-Wille distribution? I am not aware of this. If somebody is knowing this, kindly let me know. I have not gone in any literature where I have read about discrete counterpart of Cohen or Wigner-Wille distribution. Next, important transform which is used for the continuous time signal, it is called fractional Fourier transform. So here the bases are okay. So I won't go into the detail of this fractional Fourier transform, and there is a discrete counterpart of fractional Fourier transform which is called discrete fractional Fourier transform. Other popularly used transform for continuous time signal is chirplet transform. I am not aware about the discrete counterpart of chirplet. So I am putting the question marks here. If somebody knows, I would be very happy if somebody answers me about the discrete counterparts of Cohen and Wigner-Wille distribution and chirplet transform. There is very important transform which is used in compression and optimization. This is called KLT. So the full form of KLT is, I'm writing here, Kornhen-Lowe transform. I don't know how to properly pronounce it, but it is uh, known as KLT. I don't know what is the continuous counterpart of KLT. Now there is one more important transform, which is the transform from time domain to time domain, and it is called Hilbert transform. And you can have the discrete version of Hilbert transform as well. So Hilbert transform, and its discrete counterpart is called discrete Hilbert transform. So these are the some very important and popularly used transform for continuous time signals and discrete time signals. So I think I have answered all the questions raised by you regarding my lecture on introduction to Z transform. I stop here. Thanks for watching.